we'll go into a typical scenario of two-factor authentication. So when you want to log in and you have two-factor authentication, the first step is you enter your credentials on your device. It sends to the server, and then the server generates a one-time code. That one-time code is sent to you via email or messages or any other way. You input that, send it back to the server, and if the two codes match, then you're granted access. There are a few things to make sure to have this system work correctly. One thing is rate limiting. If you allow the user to input infinite tries, eventually they're going to guess the right one. Another thing to make sure is that it should be completely random and not predictable. However, this approach needs that your device that receives the code needs to be online. And it could also mean that if it's on an email and someone gets access to that email, you're compromised. So before I go into offline two-factor authentication, I'll do some cryptography background. We're going to start with symmetric encryption. For symmetric encryption, we have a shared key. Let's create a scenario. Our scenario is this guy, Scout, and Sniper want to communicate. So both of them have the same key, same copy of the key. But we also have this blue spy. He wants to find out what they're talking about. Scout has a message he wants to send. What do you think it says? It gets encrypted with a shared key. It goes over. And then the sniper can just decrypt it because he has the same key. Now, even if our spy was able to intercept the communication, he wouldn't know what it says because it's encrypted and he does not have access to the key. Can anyone think some disadvantages of this method? Yes, Brian. Exactly. You're the same thing? Yes. For symmetric encryption, typically it's really fast compared to asymmetric encryption, but both of them need to have the same key. The solution is something called Diffie-Hellman secure key exchange. I wouldn't go into details, but this is a method that allows two people to share keys through an insecure channel. So I think Trevor did a presentation on it last fall. That's probably on our YouTube. Now we've talked about symmetric encryption. Next thing is hashing. Hashing is a step of converting data of any size into a fixed size, almost random looking series of bits. So this is 256 bits. No matter what the size of a document is, it's always going to output 256 bits. It is deterministic. If you put the same input, it's always going to have the same hash. There can be many hashing algorithms. You can make up your own hashing algorithm, but there are some properties that a good hashing algorithm needs to follow. First thing is collision resistance. The likelihood that two different pieces of data produce the same hash has to be low. Even though it's not possible that there are no collisions because 256 bits can only store limited data. But if it's uniformly stored, if let's say every hash has an equal chance of being picked, then we would have low chance of collision. The second thing is a pre-image resistance. If I give you a hash, you should not be able to guess what the data was to generate the hash. In other words, it's one way and non-reversible. And the last property is second pre-image resistance. It is if you know the data that produces one hash, you should not be able to guess another piece of data that would produce the same hash. Now we're going to talk about how these concepts are used in offline two-factor authentication. Now we have the same scenario. We have a login portal, the server, and a device that we're going to use to authenticate. In this scenario, the server and the device coordinate on a shared key. This key is securely stored on the device's hardware that cannot be extracted. Most modern devices come with specialized hardware that can store encryption keys, which cannot be extracted by anyone. So this is kind of the system apps like Google Authenticator use. So now we can imagine a scenario, the device that we use for authentication does not have any internet access. So a typical authenticator app works with it every 30 seconds or so, it creates a new code, and that code is what you enter on your login portal. So the way of generating is we first find the times, take the timestamp, the current timestamp, combine it with a key, and hash it. All of it is a deterministic process that only depends on the current time. We then truncate this hash, meaning that one way could be we just keep the last 4 digits, or just take a modulus with, let's say if you want 4 digits with 10,000, if you want 5 digits, then 100,000. But we convert this hash into a 5-digit code. We enter this 5-digit code on our login portal, goes back on the server. Server also takes the current timestamp, combines it with the shared key, hashes it, and then truncates it. And if it matches, you granted access. So I've missed a crucial step, and who can think what would go wrong in this thing? What if yeah, one thing is time is not synced. That is something that you have to assume, because if you change the device on your phone, Google Authenticator will stop working. The place it would, so the step I skipped that would make it fail is there's going to be time difference, right? By the time you enter the code and it reaches the server, the time's going to change. So that's why we don't directly use a timestamp, we use time intervals. Let's say we have a 30-second time interval. So we take the current time, let's say divide it by 30 seconds, find the closest integer value. For that 30-second time slice, the code is going to be same. So that's why on apps like Google Authenticator, you have expiring codes. So in a practical implementation, we don't use direct encryption. We use specialized hashing algorithm that combines a secret with a timestamp or any data, but this is just an easy way to visualize it. That's it. Now back to Eunice. He's gonna do his presentation. Yep. I think the most typical is 30 seconds. So you know like what Unix time is? Yeah, so basically it is an integer representation of the current time. So just how many milliseconds it's been since epoch. Yes, exactly. Now, if you divide it by 30 seconds and then float it to an integer value, then for 30 seconds, that's going to be the exact same value. I mean, until we go from 0 to 30, it's going to be same. As soon as you go to 31, it's going to change. You'll always have one cutoff where it changes.
Does anyone else have any questions for Prem or?